Okay, last thing that we will use is process capability ratio, okay, that we show it with CPK. Process capability ratio, it also considers the centering of the data. I already explained what does it mean centering. Okay, this also consider the centering of the data, how far they are from LSL or USL and how far they are from the center. Okay, this is another parameter. CP, the first one, process capability potential, is a difference between these two divided by 6 sigma, and it doesn't consider really the centering, but this one will consider the centering. And as you remember, I said that sometimes CP itself alone is not enough, is misleading. We need to calculate some additional parameters, that one of them is CPK. Okay, so it doesn't take into account, CP doesn't take into account where the process mean is located related to the specification. If my mean is where my mean, if first of all, this is LSL, USL, okay, so as I said, like the CP only shows how the data are spread. Okay, it's spread like this or like that, but it doesn't show how the mean is located. If it's somewhere here or somewhere here, if my mean is closer to USL or closer to LSL. Okay, so this is okay, how we can know if my mean is closer to USL or LSL. We will use the capability ratio. So it's a measure of potential process capability. CP shows that potentially my process capable, but it doesn't give us a lot of information. And CPK, it considers the centering. It takes into account the centering, and it gives us some information about how the data are far from the center or not, which is it shows the actual process capability. We call it also the actual process capability. Okay, so it means based on the value that we have. Okay, actual process capability we always want the process to be both centered, and we want to be accurate and precise. We want the data to be distributed. We want the data not to be very spread, and we don't want the data to be far from the center. Okay, so these two concepts can be shown by using CPK. So how we can find CPK? For CPK is very simple. We have to calculate these two parameters, and then we pick the minimum between these two, the smaller one. When we have this and this, we calculate this one. For this, let's say you get 2, for this you get 3, so then you will use 2, okay? The minimum between these two data, you will pick it, and that will be your CPK. Okay, so now let's see what does it mean, okay? So the CPK, since it considers both LSL, USL, and the mean, so it will be sensitive to both the mean, okay, the center, and how far my data are distributed from the upper specification limit and lower specification limit. Again, the larger the value of CPK is better. The larger, better. Okay, the larger CPK value, the less variation you will find between the process output and specification. Okay, so better larger CPK, it means the data are more centered and also they are very well distributed between LSL and USL. So CPK bigger than 1 is a very capable process. CPK 1 is still capable. CPK smaller than 1 is not capable. Okay, this figure also shows it shows, like what's the difference between CP and CPK, okay, for different values of CP and CPK. So if CP is equal to CPK, we will have such a distribution. CP is 2, okay, CP is 2, it means all my datas, they are CP. If CP and CK are 2, like the datas are very well distributed, equally distributed between LSL and USL, okay, and they are far from LSL and USL. This is shown by CP, and they have equal distance from LSL and USL. They are really in the center and very well distributed. CP2, CPK 1.2. So now the data they are far from LSL, USL, they are still within the limit, but is closer to USL. Then CP2 and CPK1, now my data, they are almost attached, they are shifted again to the right, it's shifted to the right, and now is in the boundary of USL. If CPK is 0, it will shift again more, and it will pass the USL. CPK, it can be even negative value, minus 0.5. Now, most of my data is almost out of USL. Okay, so you can see that CP in all the cases is 2. Okay, which means that the data are well distributed. They are within, the data are within 2 standard deviation of the mean. Okay, but since we don't have any additional information, once we have CP, we can have all of this situation. But that is, as I said, that's why we are saying CP alone is misleading, because CP only shows how the data are distributed from the mean. Okay, in all the cases, they are very well distributed within 2 standard deviation of the mean, which is good. The 2-3 standard deviation from the mean is good, but CPK also give us some information how data are well distributed between LSL and USL. So most of the time, we need both these 2 parameters together to have both these parameters together to have a final conclusion of if my data are very well distributed or not. So this is the best case. This is the worst case. Okay. So the ideally CP equal to CPK is the best. Ideally we want to have CP equal to CPK, and this is the ideal case that we have such a distribution. CPK is smaller than CP, like all these cases. CPK is smaller than CP, we have off-center data. Yeah, the magnitude of CPK to CP, the magnitude of this ratio CPK to CP. So if it's 1, is good. If is smaller than 1, is not good. It shows it. If is smaller than 1, like the other cases, it will show. It can be even negative, right? It will show that if is 1 is perfect. Is good. CPK to CP, if 1 is good. If it is smaller than 1, is not good, really off-center process or data. Okay, another example that I just find it on internet is this figure. So now here, both CP and CPK will change, right? So even as I said, you remember, CP bigger than 1 is a capable process. CP smaller than 1 is CP bigger than 1 is a capable process, which is good. Okay. CP smaller than 1 is not capable. So here you can see what's the difference between in different situations. CP2 and CPK2, this is the ideal case. Data are very well distributed. This is consider this as your LSL, and this is your USL. Okay, consider it like that. This is ideal. CP1, which is in the boundary between bigger than 1 and smaller than 1, and CPK1, we will have such a distribution. Again, the ratio is 1. They are equal. Okay, they are equal. So that's the ideal case. So is again the data are centralized, but they are centralized, but they are in the limit. They are really in the boundary. The data are really in the boundary. That because CP is 1. CP is smaller than 1, which is not good because we will cross the limit, okay, which is not good. So again, but the ratio is 1. They are the same, so it means they are very well centralized, but CP is smaller than 1. We are crossing the boundaries, the USL and LSL, which is not good. CP1, CPK 0. Again, okay, is 0 is off center. Okay, the ratio is again is not good because we are crossing the boundary and we are off center. Here we are in the center, but we are crossing boundary. Here we are off center and crossing the boundary. This case, CP2, which is good because we will be still in the boundaries. CP bigger than 1 is capable. We are still within the boundary, but we are off center. The ratio between these two, the ratio between CP and CPK is 0.5, which is off center. You have such a distribution. And finally, CP2, CPK 0. Although CP is bigger than 1, which is good, but CPK is 0, it leads to something which will be out of the limit. So for knowing if a process is capable or not, we need to have both of them and we need to compare them together. Okay, that's about this part, and this is my final slide in this part. And what we are going to do here now is to do some calculation for CPK. So, example, a company that manufactures copper wire spool must produce spools with a very specific mass range. 50 samples, so we have a lot of samples. As I said, when we have a lot of samples, the standard deviation that we need, which is the standard in the equation, which is the standard deviation of population, will be the same as the standard population of samples, and the mean that we need in the equations will be the mean of samples. That's why they mention 50 samples, 80 samples, because they want to make sure that we can have this assumption. So the following data are given: LSL, USL, S, and mean. So you have the mean, you have the standard deviation. Alright, calculate CPQ. Very easy, very straightforward. You have to use this equation that you have in previous slides. Mean LSL divided by 3 sigma. You have to pick the minimum of these two numbers. USL minus mean divided by 3 sigma. So I just put all the data that I have here. I have mean, which is 561.16 minus LSL. What's LSL? 557. 3 times 3.503. And I have USL, which is 568 minus mean, which is 561.16 divided by 3 times sigma, 3.507. So I have to pick the minimum of these two numbers. So I already calculated these two parameters, but you can double check my calculation. If you see any difference, make sure that you are doing the calculation right. So the first term will be 0.39. The second point will be, what's the second point? 0.65. I have to choose the minimum. That will be my minimum here. So CPK is how much? Is 0.39, which is smaller than 1. Okay, so I can say that already process is again is for sure CPK is smaller than 1, so it for sure is out of the center. Okay, I can say the process is not capable, but let's calculate also CP to see what will be CP. CP is USL minus LSL divided by 6 sigma, right? 6 sigma. This is 6, number 6. Let me 6 sigma. USL 568, LSL 557. 6 times sigma. 6 times sigma is 3 points. The standard deviation 503. So I haven't calculated that. Just let me calculate it right away. So I'm now calculating it. You can also calculate with me. 568 minus 557. Divided by 6 divided by 3.503, that will give me 0.52, which is smaller than 1. So both CP is smaller than 1, process is not capable. CPK is smaller than 1, process is not capable. The ratio between them, CPK over CP, is going to be 0.39. As I said, we will choose the minimum between these two numbers, a smaller number. 0.39 over 52, that also gives me 0.39 over 0.52, gives me how much? 0.57 is even smaller than 1, that again is not capable. So we have all these observations that tell us that the process is not capable. Okay, CP is smaller than 1, CPK is smaller than 1, the ratio between two is smaller than 1. So you know, like, which case it can be. It can be a case like this. Okay, it can be a case like this. Okay, so CP is smaller than 1, CPK, no, it's not even this case. It can be, actually I don't have it here. Let me check this. Yeah, we don't have it here, unfortunately, but it's in the case that is a case CP is smaller than 1, like this. Okay, that is crossing the limits, and CPK is also smaller than 1. It means that is kind of, it can be, let's say, it's something like, it can be something like that. If we have, instead of 0, we have 0.3, 0.4, it will be something like that. Let me just clean this slide. So we are having this case. I can show you what case we have. Okay, we have CP 0.52, which is not capable, CPK 0.39, and the ratio between them, CPK and CP, what's the ratio between them, is 0.75. 0.75. So we have such a case, something similar to this. We have CPK 0 is here, CPK 1 is here. So it will be a case like this. The center is here. And is something like this. Can be something like this. No, sorry. Is something like this. Is such a case. So we have CPK 0.5, CP 0.5. So it's because of the CP smaller than 1, it will cross the limit. Because of CPK smaller, CPK smaller than 1. The ratio which is smaller than 1, it will be also off center, and also it will cross the limit. So hopefully you could understand this example. And okay, summary. That's the last slide we have. Okay, for the process capability indicates or indices. So we assume that, first of all, we assume that we have a normal distribution. It means all the parameters that we use, the mean, the standard deviation that is given, we will use it for population, as population mean and standard deviation. So this is valid when we have really a big amount of data, we have a normal distribution. And when we talk about process capability, we already consider that process is in control. Okay, and in case of two-sided specification, the process means centralized between the upper and lower specification. Okay, this is not something new, just saying that if we have both upper and lower specification limit, ideally we want our data to be centralized in the center with the same distance from USL and LSL. You have example 13, last example. You have all the data here. This is your okay, this is your standard deviation. Okay, this is your standard deviation, mean, upper specification limit, lower specification limit. Target value is the target value you want. You want your mean to be 8, this is not important. So you have a standard deviation, you have mean, lower specification and upper specification. This is not important. So just go calculate this parameter and then make a decision if the process is capable or not. I will leave this example for you. Please work on it. If you have any question, I will be happy to help.